So I'll talk about language design, and I'll tell you how to do it. But first, a quick question. How many of you have ever designed a programming language or a language feature or plan to do so? Less than I expected, but maybe the others will get inspired and also design something. Okay, but to those who raised their hands, we have to talk. While you were designing your languages, I was working in an IDE, IntelliJ IDE. I was trying to support those languages. Some of them directly, and some indirectly by discussing it with colleagues. And it turned out that many of the languages are not very easy to support. Many actively resist any kind of IDE support. And therefore, I have a suggestion for you. Why don't you design your language in a way that's easy to support in an IDE, in an IDE-friendly way? In return, you can get a really nice, feature-rich IDE plugin for your language, which works fast, works reliably, and everything is great. And I'll tell you how to do that. But first, I'll tell you what I mean by IDE friendliness. So, an IDE has many features, but we consider some of them more basic than others. These are listed here: editing, formatting, highlighting, navigation, code completion, and notably find usages and rename. These are all very basic features. And then, if we have all of that, we can quite easily add more advanced features on top of that, like 30 more refactorings, many inspections with automatic quick fixes, very advanced data flow analysis, very advanced debugger features for with special support for future streams and whatnot, detecting duplicate code, and so on. But this all requires these basic features. So, an IDE-friendly language is a language for which these basic features are relatively easy to support, so it takes not much effort, and the result works fast and flawlessly. And I will mostly talk about IntelliJ architecture, but I believe that the issues that I'll discuss, they are more or less common in other IDEs and static analysis tools. So, without further ado, here's a recipe for an IDE-friendly language. It consists of 5 simple steps. First, an IDE needs to look at your source code and recognize which syntactic construction is used there. Just so easy. Second, after it has recognized the construction, it needs to understand if that construction declares anything, and if yes, then what. Which names are declared and which kinds, like classes or methods. Syntactic construction can also refer to something. In that case, it would be nice to know the names of the things it refers to. And for references, it would be also very nice to know how to resolve them, where approximately the declarations could be. And finally, the last but very much not least point, so it deserves the number 0, is that all of this should be possible by just looking at one file's content. It applies to all these points, except maybe for the point about resolve hints, where it's not obligatory, but still would be very nice to have. So, let's look at these points in more detail. let's start with the point 0. By single file's content. Why do we need that? What is this, and what happens if this is not true? So we need this because then we can treat each file separately, load its contents, parse it, extract all the information about the declarations and references, and store it into an internal database called index, and then quite efficiently use it. And we treat each file separately to be sure that we can invalidate all this cache in the database when this file changes and not anything else changes. Okay. And here's a simple example from Java. A simple file which declares a class named foo. We index that information. It also extends some class named bar. We have this. We don't know where this bar is declared. We don't know its qualified name because it's not written in this class, in this file. But we nevertheless can index this information, and it's quite enough because we index also all the import statements and the package, and then when the time comes, we can resolve that superclass reference pretty fast. This is a good example of determining information from single file's content. Unfortunately, it's not always so good. Even Java has its problems. To even start parsing Java, you need to know how to parse it. Namely, which version of Java is used. In some version, assert and enum are keywords. In some other version, those are just plain identifiers which can be used like references. And this information is not stored in the source file. It's stored somewhere in the project settings. And so we need to keep additional tracking of all those settings and see if it's changed. Then we should invalidate the cache for all Java files, at least the affected ones. And that takes quite some amount of effort. It's basically the common pattern to this, to this talk. If you are IDE-friendly, then the IDE support is very easy to add. But if the language is not so IDE-friendly, then we, as IDE authors, will spend more time just supporting these basic features, and the result will probably work not so efficiently as it could work with an IDE-friendly language. So in this case, we have to spend additional effort on tracking the changes to the Java source version and then to re-indexing everything. But that's not totally bad. What's totally bad is C and C++, because it has this include directive, which just takes some file and includes it verbatim. And this can affect elixir and parser and everything. And the problem is that if this file foo.h is included into 100 other files, and you go into that file and start typing there, we need to basically invalidate all the caches for all those 100 of files and update them. And reparsing all of them isn't usually a very fast process. In addition, we as IDE vendors have to track where this foo.h is included and where it's not included to avoid invalidating the caches for completely whole project. So this means more efforts for us, and in the result we get less resources to spend on more advanced features. Okay, that's all about single files content. Next point. By looking at a piece of code, you need to know which syntactic construction it is, because otherwise you cannot start even analyzing the code. how to do it when the syntax is unclear. And here is a very nice IDE-friendly example of a class with a method, with a statement, with some field access, method call, and so on. All syntactic constructions are clear. What could possibly go wrong? It turns out that a lot of things can go wrong when determining a syntactic construction from text. First, your syntax might be completely scrambled beyond any recognition by templates, macros, or preprocessors, and so on. Take, for example, JSP. Look at what this evil JSP does to poor innocent HTML. If you remove all the markup, you just end up with the HTML with some holes, and you don't know what's in these holes. There can be some markup there, or maybe not. And it's not very clear how to even start supporting such things. Or in C++, again. There is a nice directive called define, and when you're having a define, you can do absolutely anything. For example, multiply 6 by 9 and get 42 instead of 54. Because what looks like multiplication is in fact 2 additions. Great, but that's not all. Sometimes you have binary operators that look like binary operators, but they're still hard to analyze because that needs more information not available at the parsing moment is needed. For example, languages like Swift and Haskell, they have custom operators. And here's a simple Haskell construction with A, B, and C, and some very cryptic operators between them. And you need to decide how to parse it. It can be either like on the left or like on the right. And it turns out that this is impossible unless you go to the declaration of those binary operators. These come from the standard library, but you can redefine them in your own code. So you should go to the declarations and see see the additional annotations there, which specify the associativity and the precedence. And in this particular case, I think the variant on the right is correct. But if you have to go to the declaration, first of all, it's more effort. It takes more CPU time. And second, the declaration can easily be in some other file, and so you're breaking the rule number 0. And if that other file changes, you have to invalidate all the usages of those operators as well. Great, but that's not all. Haskell is a very nice language, but unfortunately also very complicated. Not Haskell itself, but the GHC compiler. It has gazillions of extensions. Some of them affect syntax. And when you have to support all of them, especially the one named CPP, which adds all the C++ maintenance to Haskell. If you have to support them all, they start to interact in weird ways. And you end up spending all of your time just writing a parser for taking into account the potential extensions. Not to mention that these extensions are not always written in the same file, and they can be written in some other place. Very nice. Yeah, and if you spend all the time on parsing, you don't get to more interesting features. Next, parsing can be just slow. C++ again. Its templates are rumored to be Turing complete, and their compilation can take a corresponding amount of time. And it's already bad in the compiler, but it's much worse in the IDE because users constantly type something, and then you have to reparse and reanalyze that all. So people are just waiting and waiting and waiting. And finally, the syntax can be just ambiguous. I'm not talking C++, it can be cured. But even Java. In Java, syntax is unambiguous unless you are an IDE and the user is in the middle of typing something. And then you should be able to guess what the user is typing. And that's where the syntax is really ambiguous. For example, the IDE has a nice feature. When you type an opening construct, it automatically inserts the closing construct character. Like you're typing a quote and it inserts a quote for you, and you get a nice little empty string literal. And now enter Java version, I don't know what, raw string literals. You type a backtick, and the IDE helpfully inserts another backtick. But it's not an empty string literal. It's a string literal that actually starts here and goes up to the end of the file where it ends with a syntactic error. And because of that, all your code is incomplete. It's highlighted with tons of syntactic and resolution errors, and people wouldn't like that. So we had to invent a workaround for that. Another ambiguous construction. You type X and then this little sign, less. You might want to type just a binary expression, X is less than something. Or it might be a generic type declaration. And in this latter case, the IDE should insert the closing angle bracket for you. But how to know what you're typing? It turns out that to be sure if it's a type or not, you need to take this X and resolve it. And reference resolution can be quite long process, and so the user who's typed just one character might need to wait until the IDE determines if it's a field or a class and decides whether to insert the closing angle bracket. Okay, so hopefully I showed you that determining syntax is not always easy. Let's get to other points. Assuming we have completely recognized the syntax, does a specific syntactic construction declare anything? Why do we need to do that? Because we have this nice functionality like go to symbol, go to declaration, and we want to show these suggestions there. And here's an example from Kotlin, which shows a nice language feature which I'd be delighted to see in Java. So, but it also shows that the declaration does not need to be explicit. Not everything needs to be written. So this one line of code manages to declare a whole lot of stuff. Okay, it's obviously a class and a property, but it's also a field in Java. It's a getter and a setter and another component and a bunch of other methods. All this is declared, and all these can be recognized by looking at just the file's content. And it's nice. And here are some cases where it's not so nice. Okay, you've heard the talk about JRuby and seen some examples there. I'll show you another dynamic language, which we all love very much. It has namespaces, it has classes, everything good so far. But then it has some special method calls. And after you call this special method, you suddenly get yet another class named n/bar, and you can use it, and people expect it to be completed and renamed in the IDE, and references to be searched, and so on. And since it's a normal function call, you can wrap it in another function and pass arguments to there, and we have some PHP frameworks that do precisely that. And the result for the IDE is that you have to track all suspicious method calls. And these method calls can be spread across many files, and you have to track all that. And you also have to hope that the arguments passed there are string literals and not something calculated at runtime. And to do all that, you obviously need first to support that, preferably without bugs. So you spend time on that, and in the end, it doesn't work very fast because it has to traverse a lot of stuff. Okay, that's one way where declarations can be not obvious. Another way is compiler plugins, which is how they're called in Scala and Kotlin. In Java, they are called annotation processors, or maybe intrinsics. But yeah, a good thing about annotation processors is that they're not used very much. But then there is also Groovy, where they're called AST transformations, and they are used much. So you have just a normal class with a field, with a couple of fields and getters and setters for them, it's all okay. And then you have another class which is completely empty but has these special annotations that makes this a builder class for a class person. And this annotation adds some new methods to this person builder class, which you can happily use. And people also expect them to be supported, for the navigation to work, for the refactoring to work. And the problem here is that there are many of such AST annotations, and the best way we have found to support them is to duplicate their logic in the IDE. Kotlin is faster here. It allows, not faster actually, but more flexible because it allows you to reuse the code of the compiler plugin in the IDE context. It's very nice to have, although you have some performance penalty for that. But in Groovy, we just duplicate everything. We'd love, if such things has to exist in the language, we would love to have some declarative description of how it exactly works. Okay, that's all about declarations. Now let's go to the references. So, by looking at a piece of code, at a syntactic construction, we should be able to recognize if it refers to something, and if yes, then which names are referred to. And we need that for find usages, because if we have a code like this, it has 3 references, system, out, and println. When indexing, we don't know what these refer to. We know that println is a method, but system can be a package, for example. But when we search for usages of something named system, we quickly access all the files which have this word and try to actually resolve this reference and see if it points to the system we are looking for. Great. How could this go wrong? Take this Java example. It has 2 references, A and B. But unfortunately, sometimes it has yet another one reference. Who knows which one?
This.
Sorry?
This.
This? No. No. This is not an interesting reference because you don't normally search for its usages. It's Java. Right. So if this can be a string concatenation, which you cannot be sure about during indexing, because knowing the types of this A and B can require reference resolution and go outside of this file. So yeah, if it's an object concatenated with a string, there is an implicit toString call, or maybe string value of, if it's null. And people, some people expect that when they search for usages of toString, they expect to see such things. Okay, it's in Java. In other languages, it gets a bit more complicated because there can be indeed operator overloading, so it's a plus method. In Scala, it can be a plus method plus some implicit conversion to a type which has this plus method. And this implicit conversion might not be even mentioned in this file at all. And the problem with this is that if we want to find usages of such things, we basically have to remember all the places where in the project plus is used, and then just enumerate them all and check. And this is taking crazy amount of time. This, by the way, also happens with normal method names. For example, methods like add, which are very frequently used in the projects, and their find usages is also known to be quite slow. And we'd be delighted to use the compiler information, read the bytecode to see if it's correct method add, if there's toString called involved. And guess what? We do it. But unfortunately not always, because the code is always in change in the IDE, and the compiled classes can be out of date or completely missing if you use custom build system. And so we have to work over source code as well. There's also another case named Java lambdas, when something is referred, but its name is not mentioned anywhere. Take, for example, this nice interface, action, and suppose you want to see where it's implemented. If the implementation looks like an anonymous class, it's very easy, because we just, during indexing, we see this action name, and your project probably contains some 50 of those anonymous classes who mention this action, and we just traverse them all and check if they implement this action and not some other action. But unfortunately, enter Java lambdas. Now you have something like this, and in your this can be an action, but it might be something else. And your project might contain 10,000 of such similar things, and most of them will be runnable. And that's the problem, because this action is not mentioned anywhere in the file, so we cannot easily determine which type this lambda has. We have some optimizations in place. For example, we check the number of parameters and potential return types, but it's still searching for functional interface implementation takes quite a lot of time. And by the way, other languages with functional types don't seem to have this problem because in Java these interfaces are typed, but in other languages it's just a function of something, of an int to a string, and nobody in their right mind usually searches for that. But yeah, lambdas are complicated, but method references are even more complicated, because in lambdas you at least see the number of parameters and can optimize based on that. But on method references, you only have the name of the reference, and you don't know how many parameters, and this name can resolve to something outside the current file, and so it's very, very slow. Okay, so the result is that if your language requires that you write types explicitly, it's usually a good thing. for an IDE, at least. Okay, the next and the final point is resolve hints. When you have a reference, it's nice to have an idea where to look for the declarations. And we need that for a lot of things, for go-to-declaration functionality, for highlighting to work faster, and for everything else, including find usages and refactoring, to also work faster. And the less places where to look for the declarations, the faster we can check them all, and the better. And that's also, there's also a huge argument for static typing, because it's very good for a reference to be resolved unambiguously. In a static typing, you have a language specification with nice rules how to resolve a reference, and we can just follow that. But in a dynamic language, first of all, the declaration can occur anywhere in the project, and if there are several declarations with the same name, then you, in many cases, can't be sure which one does this reference refer to. And if you try to rename one of those declarations, the IDE might update usages incorrectly and break your project. So the only way for reliable refactorings that I know is to have static typing. And by the way, it speeds up things a lot. Okay. Let's look at examples. And the very best reference resolution that I know of happens in the most statically typing language, well, real-life language, really used, Haskell. In Haskell, when you see an identifier and you want to resolve it, you just take the syntactic tree and go up that tree and look for the declarations, and when you find something of the same name, that's it, like here, for example. If you haven't found anything in this file, then it's probably in the imports. And if you haven't found it in the imports, then it's in the standard library. That's it. That works very fast. And that's the ideal. In Java, things are a bit more complicated. So suppose you want to resolve this method. But you can't just start resolving the method. You have to resolve whatever comes before the dot first, the qualifier. And the declaration for this qualifier can be contained in a number of places, which you have to look all, to traverse all. So it can be contained in the inner class, in the super2 class, in the outer class, or in its superclass, or it can be in the static imports. In languages like Groovy, you have to look at category classes. In Kotlin, you have to look for extension methods as well. In Scala, you have to apply potential implicit conversions. And this all costs some time. And this makes highlighting and completion and other features slower. But, yeah, and to add to all of this, this qualifier can be declared in several places. There can be method overloading, and you also have to choose, in that case, which of the competitor declarations is more applicable. And to do that, you have to look at the qualifier arguments to get their types and to decide which one fits better. And only after that you can take the qualifier type and look for the method, for the needed method in it or its supertypes. But even taking the qualifier type can be an issue, even in Java, because this qualifier type might not be written explicitly. If you have this some method, its qualifier is v, and yeah, this v is a var, and to determine its type, you have to look at the initializer and take its type. And of course, it can be, it can also depend on another variable with infer type, and so on and so forth, quite deep. And so this seems like a nice, a big amount of work to do. But local variables are relatively fine, manageable. What can be worse is that sometimes some languages allow to emit types on the methods. So, for example, to get the return type of this function called method, you need to look at what's in the body, resolve all of that, and get its type. It's okay. So you resolve this method too, and find out that it also needs some return type inference. And so you go inside and see 2 more method calls. And this is a place where you can easily get exponential. The whole process can be complicated by generics, which might require some type inference inside, and also to call by, it can be complicated by calls to other classes. So I would recommend that return type inference is a very nice feature for private methods, but having it on something that can be called from outside might be not a very great idea. Because first, it makes the code less readable, at least to my taste. And second, it means that when determining the type of method tree, you need to go to this another class to load its text to see what's inside this mx method and to resolve a bunch of stuff there. And of course, it can be unfinished. You can be unfinished there. You might need to resolve, to go into other methods and other files and go deeper and deeper. And in some moment, you find that you need to go into another language and call a method from there, and the type is also not written there, and so you need to do some type inference in Scala, and you also go deeper and deeper and deeper there, and hopefully none of these methods fall into endless recursion mutual, and hope that you don't blow up the stack in the process. So that's quite a lot. Okay, so as I said, macros are evil, preprocessors are evil, method return types no go. What else have I said? Implicit references, operator overloading, this is all very evil. Don't do that. Do I sound like a doctor telling you not to eat anything tasty because it's unhealthy? Programming is definitely evil. The less code, the better. But yeah, so these are some constraints that make the code, that can make your language more IDE-friendly. And in fact, you can think positively about it, because there are studies saying that constraints actually can improve your productivity, creativity. So think of it as a challenge to design something cool, beautiful, powerful, expressive, concise, and yet IDE-friendly. Isn't it great? I would be especially amazed by IDE-friendly macros. So, yeah, another thing I should say, that of course this is not a must. These are soft constraints. Even JetBrains' own language, Kotlin, isn't 100% compliant to these constraints. There are always trade-offs to be made. If you decide that language expressiveness is worthy of some little amount of additional effort on the IDE side, yeah, why not? Go for it. But you should be aware of this trade-off you're making. And you should probably estimate the amount of IDE complication so that it doesn't become impossible to support your language feature. But I would nevertheless advise to follow these constraints as well as possible, because then the basic support for the IDE will be really really easy to add. And that means that as a result, we will spend just a tiny amount of our time on these basic support features, and all of the remaining time will be spent on advanced features. And language, that will probably mean that you'll have very good tooling as an IDE plugin for your language, and maybe that will mean that you will have more adoption for your language. Even if you hate IDEs yourself and think they're bloated and needed and so on, there are people who don't think so, and they need those IDEs. So here are these 5 points, and we'll just look a bit more why they make the IDE support, the language IDE friendlier. So clear syntax, it allows to relatively easily add some basic editing help, formatter, and yeah, enable all other features. If you have declarations that are clearly visible, then we can provide very fast navigation. If we have references that are clearly visible, that improves the speed of find usages and refactorings. If you have good resolve hints, it improves the speed of find usages and refactorings by a factor of, I don't know, 100. And it also improves the reliability of those refactorings, for example, by static typing. And if you can do all of that by single file's content, then we get, internally in the IDE, we get less cache invalidations, less cache recalculations, and in the end, we get better performance and more quality, more user experience quality, sorry. And final thing to say, I also believe that these 5 points not only can make the IDE, make a language IDE friendly, they are quite correlated with making the language people friendly. Friendly to the programmers who use that language. If you have declarations and references written explicitly, if you have types written explicitly in the right amount and not everything inferred, if this all is not obscured by macros, this makes it this can make it easier to read unfamiliar code. Think of new developers joining a large project. They know the language, but they don't know what this project is about, how it's organized. And having this explicitly written information will probably help them to get on board faster and start developing some useful stuff. And another aspect is if you have a simpler language with simple grammar, unambiguous, simple resolution rules, then you also probably have faster parser, faster analysis, and you will probably then have faster compiler. So people will wait less for the compiler and for the IDE to finally highlight your file and find mistakes there. And it will also use less CPU power. The laptop batteries will last longer. You will decrease CO2 emission rate if you care. So why not go IDE friendly? Thank you.